for the voice. Yeah, I'll probably chat with them after this class. And for next week, it's Chinese New Year Eve. I think you don't want to see me on that night. Me neither. So I'm gonna propose to skip that lecture for next week, and we will see if we need to make up. If we need to, I'll need to communicate with the admin to see at what time I can have a classroom. And normally, well, we have 13 classes, so it is 12 or 13, both are fine. So we might not even need to have a makeup class, unless you strongly request to.
No.
Okay. So yeah. So yeah, that also means that you only have this lecture to make your decision, whether you want to continue or you want to drop this course. I'm gonna emphasize that it's not going to be a difficult course. Well, you will need to spend some time, especially on the programming part. But I will try to make your effort worth it. That's my goal. But of course, it's your choice and it's your decision to make. So what I would recommend is, after this class, if you don't have any programming background, there are some references, some websites for tutorials. Don't read the books. Just go through the tutorials and look at the example code to see if you're comfortable with that kind of coding. If you're comfortable with that, I think you can continue. And let me know if you have questions. Just drop me an email. My email is on the first page. I will try to, at least for the next week, I will try to reply as soon as possible to answer your questions. And even if you think it is, it is something that you might not have enough time to spend on, feel free to just sit in. There might be something that you need that can be helpful. Yeah. Okay. So let's continue. Okay. So we have done the compilation error and linking error. Now, runtime errors and logical errors. So successful compiling and linking allows us to get an executable file, right? Something that you can run. It's executable file, just again, it's something similar to your installer of the software. Just double click, you can run it. Once you get that executable file, you're just sure that it is your program. There's no syntax error, and everything you need is correctly specified to produce your instructions to the computer. But still, there can be logical errors, right? Something is wrong in your algorithm, so that the result you produce is not what you expect, right? And those type of errors, we call them runtime errors, meaning that it is happening only at runtime. And now compare that against some other programming language like Python. In Python, there's no concept of compilation. Okay? You just call Python blah 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 .py. Maybe there's concepts already. I'm not so familiar with Python, but normally you just call Python blah 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 .py and you run the code, right? So what this Python itself is a program, right? Itself is an executable file. So it's produced by some other compilers, right? Potentially it can be a C++ compiler that produces Python. So this Python program is going to go through your code check the syntax on the fly. On the fly meaning that when it actually runs it check the syntax. If you see any syntax errors, it tells you the syntax error. If it doesn't see any syntax error, it continues running line by line of code until you see something. I mean, if you still have a syntax error, it will still tell you if there's a syntax error. If nothing happens, if there's no syntax error, it continues executing your code. But this execution, it's also doing similar things as compilation, right? It is, first of all, it reads your code, right? And then it translates that code into binary code that machine understands, right? And then it executes that code. Or it calls some binary code that sits in a library that machine understands. So if you compare these two processes with C++, the advantage is that everything, I mean, once you produce the executable, you know that there's no syntax error, there's no linking error, and everything you need is there. That's the first thing. And also, you are not spending time every time running this program to do this check, right? To do this interpretation. That's why with Python, it's not called compiling. It's called Python itself is called interpreter, right? So it's just interpreting your program and then it runs it. So you have done the compilation and it's done, and then you package your executable. So none of this compilation needs to be repeated when you run the program. So that's the major difference, and that sometimes you do experience that being much faster than running all those checks on the fly. Okay, but coming back to the runtime errors. Runtime errors are the errors that even though you're able to compile, you don't produce a result or your program crashes, right? Just crash. Sometimes it crashes, right? So those are runtime errors. And those errors are the types of errors that we don't like, right? You get the wrong number. What's wrong? What's the cause of these wrong numbers? And they sometimes you need to resort to debugging tools to identify those bugs. Those are the bugs, right? We never call a compilation error a bug. When we code, we are done. We say that okay, my code is compiled. We never say that we have done the project, right? When we get the right result, we say we have done the project. And we don't get the right result, we say there are some bugs in my code, and you need to debug, right? You need to identify where the bug is, and you need to fix the bug. So, because those runtime errors are very difficult to identify compared to compilation errors and linking errors, so we want to try to push everything that we can to compilation stage. When we build our library, when we construct our program, when we build our interface that other people might use, we want to avoid having runtime errors as much as possible. And we will see some examples of how to do that. So this line is an example of runtime error. So here, I'm defining an array of real number. Okay, double is the type of real number in C++. So here I'm saying that X is an array, and inside there are 10 elements. Okay, and this X is the name of this array. Now, the second statement is to print out, right? See out, just now we have seen, is to print out something to the standard output. And this something is X square bracket 11. That means the 12th number in this array. Okay, because C++ array is indexed from 0. So 0, x square bracket 0 means the first element of the array. 1 means the second element. So 11 means the 12th element in the array. So this is a runtime error. Why? Because the compiler, it is following the definition of the language, right? The way it uses the keywords double, what is the type double, the square bracket, all these follows the definition of the language. What is not correct is that the array has only 10 elements and you're trying to ask for the 12th element, right? That's a logical error, right? So this is the type of runtime error. And the modern compiler, actually, for this kind of problem, it is classified as runtime error, but modern compilers, sometimes they are smart enough to tell you that at compilation time. But you can do that. If you write your compiler, you want it to be smart, you can do that by checking, because these numbers are known, the compiler sees these numbers, right? And the compiler sees this size as well. So if you want to be smart as a compiler, you can actually tell. But there are some types, some kind of runtime error that is not detectable by the compiler. For example, if here, instead of accessing 12 or 11, x11, I call x and then I specify an n. I give it a variable n. Okay, and then I ask for an input of this n. So with that, the compiler is not able to tell whether this n is larger than 10 or not, right? There's no way, because this n depends on the people running the program and keying the number n. So that is also one potential runtime error that could happen. Okay, so some basic syntax of C++. We're not going to spend a lot of time on the fundamentals, on the details of the fundamentals. So I will encourage you to go through the tutorials at the end of these slides. Those on that website, there are quite a lot of these details in terms of fundamentals, syntax. We'll just run through them for the basics that we must know. Okay, so C++ is a case-sensitive language. That means uppercase, lowercase variable will mean different things. So in this case, I have a variable called x, lowercase x, and I try to print out the variable, which is a uppercase x, capital X. I get a compilation error, right? Compiler says you have an x, but it is not declared. Okay, in C++, the variable can be used only if you declare that this is the. So I have this variable, which is of this type. Once I've done that, I can start to use it. This is also the part that is different from probably more flexible language that you can just use any variable when you start using it. You don't need to declare it first. And the reason to requiring programmer to declare the variable is to be more specific about the types of the variable. Okay, because here declaration pretty much means that you tell the compiler that what is the type of your variable, right? With Python, with MATLAB, the type of your variable is determined based on the value, right? It's inferred, right? In order to infer the type, you need to spend some time, right? At runtime, you check what is the content, and it might be this type, right? Sometimes a number can be a real number, can be an integer, right? There is some rules behind this type interpretation, and that is also the cost that you need to pay to be able to stay at high level, right? So with a mid-level language like C++, types are specified explicitly, and the variables are all declared before use. And this is for the ease of compiler to produce specific way of interpretation for different variables, specific amount of memory in the stack for different variables. So, okay, don't worry about those details, but just be careful that two things for this slide. The language is case sensitive, so small case, lowercase, uppercase means different things in this language. I think that is the rule for every programming language, at least I know. Second thing, in C++, you need to declare a variable before using it. We'll come back to it, I think, shortly. Okay, now, indentation. The compiler does not care about indentation in C++. So you can format your program in whatever way you want. But us, as human, we do, right? We do care about indentation because that affects our readability. So still, we prefer to format, to indent the code in a nice way. But there are quite a lot of geeks. They are interested in writing one-liner code that does some fancy jobs. And there's even a competition for that. It's called this International Obfuscated C Code Contest, IOCCC. One-liner code. So people are trying to make some one-liner code that does fancy jobs, and nobody understands what it means. For example, this is an example. Okay. This is a C code. It's not C++. This is a C code. It's in this example folder. I'm gonna upload after this after tonight. Kernel.c, and this is the code. Look at this code. You have an entry point main, right? And then the rest of it is not humanly readable, right? But it is a C code, and it is also possible to write C++ in this way. No indentation, just one line, and does whatever you want. But it does it does produce something. If I have this one in the example code folder. So it's here. So kernel.c. Right, this is the code. And if we compile it, because it's C, so it's compiled by the tool GCC. So if I just -o kernel, and I'm using this one-stage compilation, kernel.c. I get some warnings, right? I'm getting warnings, right? Warnings, right? So it means that it is not quite standard, right? The compiler doesn't really like that, but it's not error. So you can still translate that code into binary executable file. And now we have this kernel, okay? And now let's run it. What does it do? /kernel, and let's do NUS, okay? It takes an input, and it produces these 3 lines. O. What does it mean? Anybody? What does it mean? No. Let's try another input. Math. Different O's. Any guess? Yeah, exactly. It's the position of these letters on your keyboard. The math is this is M, right? This is M, right? M-A-T-H, right? N-U-S, N-U-S. It's quite fancy, right? I mean, how do you produce that with one line, with this code? I don't know. So this is something for fun. I mean, don't write this kind of code. Okay? It's fun, but you get fired if you write that at your job. Okay? Okay. So here we are just trying to say that the indentation doesn't matter. Right? You can format your program as you like, but we do want to recommend having nice format. Okay, now comments and statements. A comment is just a part of C++ code that instructs the program to do something, what to do. And every comment must be ended by a semicolon in C++. So you see that all my code, so here this code, this whole thing is a comment. So from here to all the way to here. And after a comment, you have a semicolon to specify that, okay, that's this comment, and then next one. So here it's also the same. It is a declaration of the pi, and they initialize the pi to 3.14 and end it with semicolon. Okay, so that's an instruction to tell the program that I'm declaring a variable called pi, and I'm initializing the value of the variable to 3.14, and that's it. Statement block is just a group of comments, and you bracket the group of comments by a curly bracket, and that's a statement block. So just a sequence of comments. And in general, when we say a statement, that can refer to a comment, or it can refer to a statement block. So just statement. So it can either be, this is a statement, this is also a statement. Okay. Parentheses and brackets. And we use parentheses to determine the order of evaluation of expressions, right? Similar to your math expressions. That's one use case. The second use case of parentheses is for function calls. Okay, function calls will come back. Well, we have seen them in the main function, the bracket. We'll come back to that later. And square brackets, we use that for arrays, right? For arrays and also vectors. There's a difference between arrays and vectors. We'll come back to that later as well. It's used to specify the size of the array, like we have seen in our examples, that you want to specify that an array X is of length 10. You say that, well, double X and then square bracket, double X square bracket, length 10, and that is the statement saying that, okay, my X is an array of length 10. And just now we have seen the page to access a particular element of this array X. We call that X of, let's say, I, which can be 1, right? Can be 2. So that's getting the value, the ith value of the array. And remember that in C++, the index is 0 based. So the first element sits with index 0. And curly bracket, we have seen that it was used for statement blocks, and it is also used to define scopes. What is a scope? We'll come back to that later. Angular bracket is for template parameters. Again, we will come back to that later as well. Yes. So comments in C++. Comment in general for programming language is the part of the code that can be ignored, that should be ignored by the compiler or by the interpreter, right? It's something that you write just for human, for yourself, for your colleague, for future users of this code. So every programming language has a way to specify, okay, this part of sentence is a comment. Okay, the C++ C++ way of stating that is, there are two ways. One way is use double slash, and everything for this, for any line, if this line has a double slash, everything after this double slash is a comment. For example, like this, right? Double slash, and then you write whatever. This line, the whole line the part of the line started with double slash is going to be ignored by the compiler. Right? Just throw it away. There's a preprocessing function run when the compiler translates your code. The first thing it does is to just throw away those comments, because those mean nothing to the computer. Just it's something for human. And the second way for C++ to state comment is this, a pair of slash and star and slash. I'm not sure if this is called star or not, but you see what it is. So this allows you to comment out multiple lines, a block of sentences like this, right? You have two lines of comments, and then you just place slash star and star slash. The suggestion to comment out stuff is to always use double slash. And the reason for that is these pair of comments sometimes can be confusing, because, well, I don't have the example here. So let's look at, let's just write something. So, okay, let's have one more line. 1 equals 2, 6, and std out. X minus y, std. So, okay, I'm just declaring another variable and assign 6 to it, and trying to print out x minus y. And now if I use this style of comments, okay, so I'm commenting out 2 lines, right? And now, at later stage of development, I feel that I want to actually comment out all the 4 lines. What do? I do this, right? Commenting out all the 4 lines. But now you have seen that because the definition of this comment out is that everything starts with this, so everything in between a pair of these and these gets commented out. That means this is also part of the comment that gets thrown away by the compiler, right? So you get a compilation error because you have an unmatched second half of the comment. Okay, so if you nest these block comments, you might have issues like this. So the way that we always recommend to just use double slash to comment out stuff. Of course, you feel free to use the block. Just be aware that it is possible if you nest 2 blocks of comments, you might get compilation error, which is also fine, which is easy to fix. But if you do this, comment out this part, these 2 lines, and if you want to comment out all the 4 lines, you still get the correct comments, right? Because you can ignore whatever that is after double slash for each line. Even you ignore this, is fine, right? There's no pairing of this comment sign. So yeah, that's what I was trying to say. Okay, now we have seen variables, and variables is the tool that programs use to obtain information from user, from computer files or by computation. So it's something that you use to represent a particular value, right? When you write your program, it's similar to symbols or variables in mathematical expressions. This information that you store inside this variable is usually used by a later part of the program. So you need to have some space in your memory to store these variable value, right? And the name of the variable typically allows you to find where these values stored. Okay. So a little bit about computer science. Memory, computer memory. It is the RAM, right? When you buy a laptop, it's RAM is the memory, and your hard disk is your hard disk, right? Memory is something that when you restart, it gets wiped out, and when you run your program, it's always run in a memory space. So it just it has its own memory space, and then this memory space is just a chunk of space that allows the program to store different variables at different address, and then the variable name just tells you that for this variable, when you look for the x, go there. Go, if you look for y, go there, right? So the value of y is over there. So that's the purpose of variables. And in C++, you're not allowed to start a variable name with a digit. For example, 1a is not a valid variable name. The value of the variable, as I said, is the information stored in the memory region that the variable represents. And the type of the variable determines how is this information interpreted. And when we see our declaration of variables, we always start with something like int, right, for integer, double for real numbers, and something else, some other types for something else. And this is the type of the variable. And what does this type tell us? To know that, you need to know how does computer represent numbers, right? Computer memory is a chunk of memory that is bits, right? A lot of bits. And every bit is either 0 or 1, right? And then for one variable, it can take up 8 bits, or 32 bits, or 16 bits, or 64 bits, or even more. Okay, now let's assume that you have, take an example of an integer. Normally an integer takes 32 bits. So there are 32, 0, 1, 0, 1, 0, 1, okay? And these 32 bits, what value does it represent? Let's see if I have, yeah, let's see. So let's say we have an integer that is 32 bits, and the value it represents is the binary value, right? The binary number, just the bit value times 2 to the power of the position of the bit. Okay? So in this case, this is 2 to the power of 1, 2, 3, 4, 5, 5 plus 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. So it is 32 plus 8 plus 2 plus 1. It is 43. So these 32 bits in your memory space represent 43 if the type of the variable is integer. Right? So here is what type is used for. Type tells the program how to interpret the number. Same 32 bits. If the type is a different type, if it is a double type, that represents a real number, and the real number is normally using the floating number representation. that would mean different number, right? That would mean a different value. So the type is the way, is the convention for the compiler, for the program to interpret binary bits. What does it mean? What's the value of it? So it's easy to see that integer, it's just a binary representation of the number, and we normally call this kind of representation fixed point representation. This point means in the decimal representation, it's decimal point. Here it's binary point. Integer is a fixed binary point representation, where this binary point is fixed here, right? Fixed at the rightmost position, means actually there's no fractional parts of this number, okay? And if you want to create a type that fix your binary point here, you can also do that. Well, in C++, I think there is no native fixed point representation. I might be wrong for this part. Normally I don't use that. But if you want to create a type, or if there is already a type that fix the binary point here, this number, the way to interpret it will be that for everything up to here, it is the same formula, and then you will need to add for anything that is beyond, I mean at the right side of the binary point, you will need to be calling bj of 2 to the power of minus j, right? J here being, in this case, being 1, starting from 1 to the binary number of binary point. And with this number, with this interpretation, your number can, the precision of the number, it can be up to 0.5, right? So in this particular case, it will be representing 1, 2, 3, 4. So 2 to the power of 4 plus 2 to the power of 2 plus 2 to the power of 0 plus 2 to the power of minus 1. Okay, it will be 16, 4, 1, and 0.5. So, so 21.5. Is it clear? Ready to repeat? No, it's a convention, right? The binary point is a convention that is defined for different types. For integer, the binary point is at the zeroth position, right? So you just convert this binary point to an integer following this formula, okay? Following this formula. And if your convention for your type is specifying that, actually I want to be more precise than integer, I want to be up to 0.5, I can use 1 bit to represent my fractional part of the number. So I can say I want to fix my binary point here, and everything on the left is a binary representation for my integer part. Everything on the right is the binary representation of my fractional part. So with that representation, we're able to represent something 0.5, right? So that's just a convention. That's just a type. And the whole category is called fixed point representation, meaning that as long as you specify that a fixed point representation, you need to specify the width of your bits to represent numbers and the position of your binary point. Okay, that as long as you specify both of the two variables, the number of bits and the position of your binary point, you have defined a convention that you can use to represent numbers with computer. And now, from here, you can actually see that the representation, the number representation by computer is not so precise, right? If you really want to define a precise real number, you need a lot of bits. right? And it actually loses precision, right? Depending on which type you are using, the total amount of number that you can represent using a fixed amount of bits is limited, right? You have 2 to the power of w. This is the total amount of number that you can represent using w bits. This is limited, right? And therefore, because of this limitation, when we run our program, it is possible. And with integers, it's always fine, because integers are kind of, the range is quite wide. We run our program with a real number, floating point, with a real number, with a number with a fractional part. In most cases, we lose the precision, right? And that is sort of the error we introduce in our computer program, right? So that contributes to part of the errors. And when we run our numerical methods, one type of the error is the error that is introduced because of the limitation of the number representation by computer. Of course, fixed point representation is not something that we use for real numbers, right? We use it only for integers, and we know exactly what's the range of the integer, and we are good with that. To represent real numbers, we use the representation method called floating point representation. So as I said, the fixed point is fixing the binary point. Floating point means you allow the binary point to be floating. It can be at first bit, it can be at second bit, it can be at third bit. How is this achieved? It is pretty much the same as the scientific notation of a number. So you can represent any number as using a scientific notation, where you specify the convention that I have only one digit at the left side of the decimal point, right? So my decimal point is actually floating, but it is floating with respect to my exponential, right? So this is floating point representation, okay? So looking at this scientific notation, what do you need to represent is the exponential, right? You need to have certain bits to represent an exponential, okay? And this is an integer, right? So this part, you use the binary representation for integer. So you say, okay, I have 32 bits, I use 8 bits for my exponential, okay? And then I use certain bits to represent this number, okay? Okay? And that is my significant, right? This is my significant. And then I use 1 bit to represent the sign of the number. Of course, for integers, there are different ways to represent negative numbers. We are not trying to understand very deep on the topic of number representation, because that's not something you will be very interested in. The reason we are talking about this is that this is the source of the rounding errors that we will see in numerical methods, and it is generally good to understand intuitively when people talk about floating point representation, what does it mean? Because 99% of the developers probably doesn't understand what exactly is floating number representation. So if you understand it, you beat 99% of the developers. Seriously, I'm talking about developers. Floating point representation, okay, there is a epsilon, there's a machine precision, there's a rounding error. What exactly does it, how does it represent? How does it represent a number? Ask your computer science friends. They might not be able to answer. Okay, but if you really just look at the idea, it's simple, right? It's just scientific notation, right? Scientific notation, and define a standard to split different parts into the total number of bits. So okay, so now we have a decimal. We have a scientific notation for decimal numbers, and the binary is the same, right? You can convert anything that is decimal to binary. So we can have a scientific notation for binary points, sorry, binary numbers. Okay, and binary numbers, what's the better part about binary number is that the significant always start with 1, right? You can always say that I'm requiring my significant to start with 1. Because any number, there has to be a 1 somewhere, right? If there is no 1, that is 0. That's a special case. Okay, so yeah, we have a special case of 0. If a number is not 0, you always start with 1. So 1 point something, and times 2 to the power of an exponent, the exponential part. So this is the exponent. I think this is, this is just a particular example. Okay. So now, how do we represent that in floating point? Because everything starts with 1, so you just say that, okay, I don't care about this 1, I assume that it's always 1 point something. So I just need a particular amount of bits to represent the things after 1 point something, right? Only the fractional part. And then I need some bits to represent my exponent. And then I need a bit to represent my sign. And that together is the IEEE 754 standard, that how do you interpret certain bits in your memory, or in that certain bits in binary form to a real number. Okay, the first bit is the sign, and then the next x bit is the exponent, and the next y bit is the part that is the 1 point y. So that's the IEEE 754 standard, and just taking that, if you want to convert that into a real number, this is the formula, right? So the sign times 1 plus significant times 2 exponent minus a bias, because you want to represent small numbers, right? So bias can typically be 1 to 7 for 32 bits floating number representation, and it can be larger for 64 bits floating number representation. So with another benefit of this floating point representation is that you have you're actually precise, very precise when your number is very small, right? You're not that precise in absolute term. You're not that precise when your number is huge, right? Look at a problem of 1 billion. I mean, at a scale of 1 billion, you don't care 5 decimal points value, right? You care about only the first probably 7 digits, 8 digits, right? And that is the part that scientific notation and floating point representation can give us, right? We put the scaling part aside, we put the exponential part aside, we look at the significant part of the number, right? So we say that relatively we are precise up to certain precision. And it is also similar in similar way that when you look at errors, it's always easier to look at error in log, right? Log is pretty much rescaling your axis by putting more numbers in the when the number is small, and putting less numbers, fewer numbers when either the absolute value of your number is large. So that is also another benefit of floating point representation. With this kind of representation, you can represent a very wide range of numbers. So here are the building types of in C++ of the numbers. The building types typically we will use is integer, And for real number, we use double. But there are other types: short, long. Short is integer. It is just a smaller number of bits to represent an integer. So the range of it is 2 to the power minus 15, 2 to the power of 15. I think there is somewhere there's a minus 1 here. Okay? Minus. And integer, 32 bits, so 2 to the power of minus 2 to the power of 32, minus 1, until 2 to the power of 32. No, sorry. 2 to the power of 32, minus 1 here. So depending on the number of bits, the range that the type can represent are different. And for real numbers, you have, well, long is the same as integer, it's also integer. So real numbers, you have float, which is 32-bit in general, and double, which is 64 bits in general. So with 64 bits floating point representation, you're allowed to be precise up to 15 digits, right? 15 digits. So your range of number can be from, well, what is this? Yeah, from 1.7 exponential to the power of minus 308 plus 308. So that's a very wide range. And of course, with that representation, it's always relative, right? So the number of significance is around 15 digits in terms of decimal representation. That is also the rule of thumb when we talk about our machine precision, machine epsilon. We say that one operation, you can be precise up to 15 digits, right? 10 to the power of minus 15 is pretty much what we can expect when we make an operation. The error can be that large. And when you have, these kind of machine epsilons or rounding errors, these are rounding errors, these can accumulate, right? And it can be accumulated, and after your complicated algorithm, a lot of procedures, a lot of operations in your algorithm, these error can accumulate to a larger magnitude. Okay. For example, if you just apply a square root, this error becomes 10 to the power minus 8, minus 7, right? So that's something that we need to keep in mind, that if we use double, we use real number in computer, we are subject to the rounding errors. And this is what could be the significance, what could be the precision of the rounding errors. And do note that all these types are operating system and compiler dependent. So different compiler can interpret it differently. Different operating systems can just define their own width of numbers for different types. And there is a built-in function called size of, to tell you that what is the size of each type. So if you run that on your computer, you will know that on your computer with your compiler, how many bits are each type use. So how many bits do each type use? So here in this program, I'm just printing out the size of chair. Chair means character. Okay, so it's just a letter. So it is. It's typically 8 bits. And size of int, size of short int, long int, float, double, W chart, and we can run that. So we have a size of here, right? It's the same code. So we do a G++ -O size of, and the size of the CPP. We can see that how many, well here the result is in bytes. Okay, 1 byte means 8 bits. Okay, so this is how many bytes do we have for different types. And Opposed to signed types, we have also unsigned types. That means we don't care about the negative numbers if we use this type. And then with that, we are shifting our range that we can represent to the right? So instead of minus 127 to plus 128, we can represent now 0 to 255. Okay. Similarly for char, for int, short, long int, we are just shifting everything to the right. And in this case, we use exactly the same formula that we specified before, that we just sum up bi to the power of I, from 0 to n. So this is our number. With types that represents negative numbers, there is some treatment for the negative part. We are not going to go into details of that, but just remember that there is some convention to represent negative numbers, and because of that, the range is split into two parts, right? And one thing we do need to take note is that if you want to use unsigned types for a better use of the total number of bits, because you know for sure that you're not going to deal with negative numbers, you still need to be very careful, especially when you're trying to make subtraction. A minus B, if A is less than B, because the type is the type is unsigned. Both A and B are unsigned, the result is also unsigned. And if you define that A equals to 4, B equals to 5, you get minus 1, right? You expect minus 1. But here, you're not getting minus 1. You're getting some very huge number. Because your type is unsigned, and you cannot represent my negative number using this type. So whatever that is produced is not minus 1, it's something. Just the program interpreted in the convention of unsigned number. So just look at this 0 and 0, 1, 0, 0 and 0, 1. It's very likely that with 4 minus 5, you get something up to 2 to the power of 100 something, or even more. Okay. So we are a bit slow today, so I'm not going to show you these cases, but you can just copy this code into the Hello World program. You can see what happens if. Okay, a variable usage. We have discussed these. You need to declare a variable and define or assign the value to the variable. The value can be changed and used within their scope. So the variable can only be used within their scope. The scope means the range that the variable can be used. It is defined by the nearest curly bracket that the variable is in, right? When we talk about curly bracket, we say that curly bracket is used to define a statement block, and a statement block is also a scope, that any variable inside this statement block is visible only within this statement block, only within the range that the curly bracket includes. You can define and declare your variable in one statement, right? Here I'm declaring A and define it to be 5 in one statement. If you want to have a variable that cannot be changed by others, you can say that it is const. That means it is a constant variable. Okay? And what's the benefit of using constant variable? Constant variable, once you declare that, you know that for sure it is not going to be changed. So the next time you use it, you know that it is, in this case, it is pi. You don't need to worry about certain part of your program. Imagine you have 1,000 lines of program and you define a variable in the very beginning. It is possible that within these 1,000 lines, there are certain statements that changes the value of the variable, right? So after all these, in the end, you want to use pi. You don't know if it is changed or not, right? Unless you just go through the program. But if you define this pi as a constant double, in this case, you don't need to look at those code. Just know that, because any statement that tries to change the value of a constant variable, you will get a compilation error. Because that violates the rule, because you are not allowed to change, and if you try to change, the compiler is going to tell you. And the compilation error is the errors that is very obvious and very easy to fix. So, and you know for sure that when you use, the second time you use pi, it will still be 3.1415926. Okay, and we have a keyword called type define. So type def to make a short name for any type. So in this case, let's say we are not very comfortable with this unsigned int, and we want to use this type just to represent someone's age. So we can define our own type. We use this type define and the actual type and the name of the type that we want to use. So after this statement, we have defined a type called age. And this type is actually an unsigned int, an unsigned integer. And we can use this type to define our variables. Okay, that is for the ease of reading, the readability of the code. Okay? And it can be helpful if your type is so long, right? Sometimes you can have a very long type that is a map of string to a map of string to a boost any. So this kind of type, imagine that you define a lot of variables of this type. It is better off to give it a name, right? And then use the name in the code. And there's a special type called enum. It's a type that declares a set of identifiers that can be used as values of the type. And internally, it is just integer. Enum, it's just a way to give a type, to define a type that can have different, a limited number of values. For example, here, we can define a type called weekday, and weekday can only be Monday to Sunday. Sorry, weekday can only be Monday to Friday, right? So there are 5 variations of this weekday. And so our weekday as a type, its value can be Monday, Tuesday, Wednesday, Thursday, Friday. Okay? Nothing else. And internally, these gets converted to an integer. The compiler is going to use integer for that, for any enum that you define. And the Monday is assigned value of 0. Tuesday is 1, Wednesday is 2, Thursday is 3, Friday is 4. Okay, so this is the enum. Of course, you can say that sometimes I don't want my Monday to be 0, if it matters. You can say, okay, I want to start from 1 instead of 0. And then in this case, Tuesday will be 2, Thursday will be 3, Thursday will be 4, Friday will be 5. It's just a way to give a meaning to the type and the variable, the value of the variable. This is much better than, if you really want to define weekdays, it's better than using integer, right? It's more readable, it makes some sense. And in our case, we will be using enum to define the type of our options. We can use co-options, we can construct put options, we give them a type. So that if my variable is of, when I define my tradable, I have one variable called option type. It can either be co or put, right? It makes more sense than having some string or some integers to distinguish between the type of option, right? I've limited my support, co or put, for an option type. And when we want to extend it, we just add more variations to the type, to the enum type, right? We can add binary core, binary put, core spread, different type of options. Okay, so scope of variables, we have discussed that. a variable is only valid inside its scope, right? So if you look at this example, I'm declaring and defining a variable a and initialize it with 1.0, and I try to print out this a outside the curly bracket that the variable a sits in. This statement is going to give me a compilation error because a is not known when at the time of printout, right? A is only alive within the statement block, and this statement block is called the scope of the variable a. Exceptions, don't worry about these. We are not going to use the exceptions. Just be aware that there are exceptions for variables like static variable or global variable. By their name, you know that it is global, right? Static means something statically stays there, so everybody can reference. Global is what this variable, even so there's no scope, or the scope is the entire universe, the entire memory space. That's by name you can infer that. We are not going to use that, and normally we don't recommend you to use that. It can be, because imagine that something that is accessible by everybody. Everybody can change its value. When you want to use the value, it becomes difficult to be sure that what the value can be, right? Unless there's a need to communicate between different part of program, and you're going to use that to specify the state of your program. But that's a little bit too complicated. And in most cases, we can avoid using those global static variables. So operators. We have arithmetic operators: plus, minus, multiply, divided, taking a module, taking a residual. Plus means increment your variable by 1. Minus is to decrease your variable value by 1. And they work only with integers. Okay? And relational operators: equal is to check if two variables are equal, not equal, larger than, less than, larger equal than, less than equal to. Be careful with this equal. This equal means bit by bit comparison of the value of the variable, right? So if you have one number that is a result of a numerical operation, another number that is a result of numerical operation, and in theory they are equal, and when you check, because they are real numbers, they are subject to rounding errors, so in practice they may not be equal, right? Just try, when you try to compare two real numbers, just always be careful about using the sign equal, right? Normally you check the absolute difference between A and B, and you check if it is less than a very small number, 10 to the power of minus 10, for example. That's a general rule when comparing equality between doubles, real numbers. Logical operators: this is and, this is or, this is not. So we want to check the condition of A and the condition B. If they are both true, that is, you use and the condition is not true, not. Bit operators, I'm going to skip. They are making logical and, logical or, and flipping the number for bits, and this is to shift to the left and right of the whole bits. We're not going to use them, but they are normally, if you have the cases that use them, they will improve the efficiency of your program, because they are really operators that is very straightforward to the CPU, what to do with this amount of bits. Shift everything to the left, shift everything to the left. Shift everything to the left means actually multiply by your value by 2. Right, because you're basically increasing the I in the formula, right, by 1. So that is, if you look at the one-liner, this kernel.c, this code, they did the trick by using quite a lot of these bits operators. Okay, but that is really if you really want to pursue extreme efficiency, you will need to consider using these split operators. Okay, assignment operator. This is to assign. This is not to check equality. This equal means assign the right hand side value to the left hand side variable. And this plus equal is to assign. So if I say fx plus equal 5, it is equivalent to x. You assign x plus 5 into the variable x. So you're increasing x by 5. Minus equal, multiply by equal, divided and equal is the same thing. Just apply this operator first to the right hand side variable and put the value back to the left hand side variable. Okay? And the sequence of operators, you don't need to pay special attention. When you are not sure, just use parentheses, right? Just bracket the operations that you think should happen first. Header files. You have seen in our Hello World that we have used this include keyword to include something from, in our case, it was IOStream, which is some header files that defines the function we use, the cout, right? The function we use to print out our string to the screen. So include, it just means that take this file, IOStream, it's a header file, it's a .h file, it's not a .cpp file, it's a header file. Take this file and copy the content inside that file and paste in my current file. So that in your hello world.cpp, actually the compiler, when it sees this include, it's the first thing it does is to find this IOStream, this header file. It's IOStream.h somewhere in your system path of your C++ library. It take the content, paste into your program, and then it start to continue its processing. And there are two ways to include. One way is use the angular bracket, and that typically is used to include a standard header file. If it is your own header file, you use quotes. There's no rule for this. You can do both, but it's a convention that when you see these quotes, you mean that this file is my own file. Okay, it's normally sitting in the same directory of yours. Okay, and include is doing the same thing. It takes the content of the file and it pastes into your CPP file. I/O, in and out. We have seen the output operator, right? It just streams the content to the output, and cout is streaming the content to the standard output, which is our screen. And we also have input operator. Input operator takes content and then assign the value of the content to your variable. And the source of this content is the standard source. The standard input is the keyboard. It can also be a file, right? You want to load something from a file, you use this input operator. We will have examples. Don't worry about that. And of course, to use these operators, you need to include the header files that defines and declares these operators. And for our standard input and output, cin and cout, it's inside IOStream. Okay, so you include IOStream. If you're dealing with files, you need to include this fstream. F stands for file. And this IOmanip provides some functionalities to format the input and output. These are not really things that are important, but it's something that you will need to use when you interact with your own input, when you take stuff from the file. But those are straightforward. Once you use it, you will know how to use them. Okay. Branching. We have if statement that allows you to branch your code into two parts, right? And in this example, we are checking if the option type is a call option, then we do something to price the call option, right? If your option type is a put option, we do something to price the put option. And if it is none of them, we throw an arrow. Throw an arrow meaning that tell tell the user that this message, right? Unsupported option type. You might wonder why do you do this, right? You do this because it is some case that you're not able to deal with, right, when you write the program. Okay? And if you don't do this, it's going to be a runtime error. And runtime error is difficult to deal with, right? So, you do this, it is still a runtime error. But this runtime error, at least you're telling them what is happening, right? This throw is going to tell them, it is the option type that is having a problem. And it's the type that the pricer doesn't support. So you are trying your best to tell the user of your code what could be wrong. If you cannot avoid putting all the errors in at the compilation stage, at least you tell them, gives them some information. But this is a way of communication between programmers, right? You throw some errors. So this is a typical practice. When you have something that you cannot deal with, you throw an error. But here, this page is more about the if statement. So if statement is clear, right? You can check if a condition, else if another condition, else. So this is just a logical way of if. There's one special operator, conditional operator, which is this. The first expression is an expression that gives the value of the expression is a boolean. So it's a condition that checks if it was true or not. Expression 2 is the value of this whole expression if expression 1 is true. If expression 1 is false, you get the value of expression 3. So this is equivalent to this, right? If expression 1 is true, then expression 2, otherwise expression 3. So this is just the return value of this whole statement. It's just a way to make your code one-liner. You can always do this. If eventually you will be, when you use this kind of operator, you'll be x equals condition 1, 1 or 2. So if condition 1 is true, x equals to 1. Otherwise, x equals to 2. This is just equivalent to if condition 1, then x equals to 1. Else, x equals to 2. It's just to make the code concise, nothing else. It's typically faster as well, but we don't really care about this kind of difference in terms of performance. Okay, and another way of branching is to use switch statement. Switch statement basically branches a variable, in our case, an option type, into different branches, right? So you check if the option type is a call option, you run this part of code. If it's a put option, you run this part of code. Otherwise, we throw, right? We throw an arrow. And the key word here is switch, and case 1, case 2, case 3, case 4. Okay, switch and case, so that you can branch from one variable to different variations of the value it can be. Okay, about exceptions. I've said that we are trying our best to give meaningful runtime errors. Okay, and these exceptions can be caught, right? Meaning that if I'm running someone else's code, a pricer, I'm feeding it an option, and if it doesn't support my trade, if that pricer doesn't support my trade, I might be getting some error, right? But I don't want that particular pricer to fail I don't want the failure of that particular pricer to fail my program, because maybe I'm running a portfolio of 1,000 trades. If I run them one by one, and one of them gets a failure, my program stops. Right? I don't want that to happen. I want to catch that exception, so that okay, it might fail for whatever reason, for whatever errors. This program is going to tell me what is the error message. But I'm going to continue. Right? I'm going to continue to finish my 1,000 valuation of my trades, so that at least I know that for the trades in my portfolio that is not failing, what are the value of them. And then I look at the error message of each individual failures for each individual trade, and I will deal with that. So the way to achieve that is to catch the exception that the other program is throwing. So throw and catch. Okay, so that's the key word. But throw is just to raise an exception. Okay, for my case, if I just run that code, if he raises an exception, if he throws, and then I need to catch the throw, right? Before I catch the throw, I need to know that okay, that code might throw, so I need to do try catch together. So that's the way to do it. Let's look at this. So switch option type, call, put, and then throw. Then how do we catch? We do this. Okay? We do this. It's not in the slide. So we do this. Try, and then catch. Exact syntax doesn't really matter. So it's this pattern that you need to be aware of. So try some function, right? Pricer, and then trade, market. And this pricer, if it throws, I'm able to deal with the exception inside this statement block, so that I don't crash my code. Okay, and I look at what is the message that this pricer is throwing, and I have my corresponding treatment for that kind of error message. And there's also a way to throw exceptions with the keyword assert. Assert, it's a function actually. So assert is defined inside this header, C assert. It's typically some preconditions that you want your function. Before you calculate anything, you want to make sure that the input is valid. In that case, you use assert. Right? You assert that, okay, A plus B equals to C. I need that to happen to proceed. Sometimes you want to assert that there's, and when you get implied Vol surface, you want to make sure that there's no arbitrage in the Vol surface, otherwise your model doesn't calibrate, otherwise your model is not valid. So make an assertion before proceeding. And the assertion, if the condition inside this assert function is not true, we're gonna throw an error. Okay. Since we're skipping next lecture, can we have 30 minutes more today? Okay. So exception. Yeah, okay, huh? Okay. So exception handling. That just now I said that we use try and catch to handle exceptions. If some other functions throw, and we use catch to handle it, right? So we try, and then the code we want to protect, and then we catch the exception. Okay, and then in this particular case, we just print it out. What is the error message? And you can do better, right? Talking about try and catch, I just have a friend. He posted a blog, and he worked for Microsoft, and he just had some joke about one of his interns. He said that he's giving the intern a task. He said that, okay, try to do some exception handling, meaning that I try to catch exceptions and then deal with that. And what the intern did was try and the code catch the exception, which is correct, and inside this catch statement, he calls throw. He calls throw E. So he was making a joke about that. So you're trying to catch something that people throw, and then you're gonna throw it away. So you're gonna raise another exception. So this part of code is still going to crash, right? Because you're throwing. So you catch a ball, you're throwing the ball again, right? So what this statement block catch wants to do is to deal with the error and not to raise a runtime error, right? Print out or do some fallback, but not to just throw an exception. Because if nobody catch the exception, the program stops, right? The whole point of exception handling is to prevent from stopping the program for cases that you know how to deal with. So you only throw if you're not able to deal with your exception. Okay? So this throwing again is like doing nothing. It's the same as don't try. Just let it throw. Okay? And there is a code written by a computer science major, right? What I'm trying to say is, it is not something that, I mean, even if you're a computer science major, like myself, after 4 years of programming, I don't really know what exactly it is. I mean, what is the logic or the principle of programming language? Unless you really start to use it in practice, I start to learn what is memory leak, what is exception handling, and these things will happen. And if it happens, you see the phenomenon, the breaks in production, the crash of your code. And once you see that, you have the experience, and you know what exactly is going on. So it's I mean, I just want to say that it's always okay not to know things, because things are, I mean, you just learn from what you don't know. Okay. The reason I want to make a little bit longer is it was too boring, right, until now. We have some example, we have some case that we can look at. So if we want to put everything together, we want to use the basics that we have learned so far to price something, right? To price an option, a one-step binomial tree. We want to price a co-option, assuming that we are under an ideal world, that our market, our stock, has only two possibilities, up and down, and we know exactly what is up, what is the price if it goes up, and what is the price when it goes down. What is the price of the option? And I like this example, I like this one-step binomial tree. It's because these words, the interview question when I go to Stanchart for interview, and this is my favorite question. I use when I interview people as well, when I interview candidates as well, and I'm able to use this question to filter half of the candidates I've seen. Surprisingly, right? It's like quant finance 101, right? And the question I ask, okay, let's try. The question I ask is always, well, I'll start with this definition. I'm starting with S0 up. So S0 is 100, SU is 110, SD is 90. What is the option of a call at a strike of 105? Okay. And okay, 20% of the candidates I see, because they are away from school for too long, they struggle a bit, because they say that there's a probability of going up of 20%, 50%, and some 20% of them use the probability, which is quite obviously wrong, because you are still in the school, right? Maybe after 2 years, you only remember the expectation. And okay, many of them are able to produce the price using different approaches. You if you remember the formula, you calculate the risk neutral probability, and you say that okay, the price is the expectation under this risk neutral probability. Okay, very good. And the follow-up question is, what does it mean by this risk neutral probability? Why it is so? Starting, to get a bit of struggle, right? And also, how do you protect yourself? How, if you are the one selling this option, how do you make sure that you don't lose any money, you don't win any money? Because you are at the role as a bank, you don't want to take any risk, right? When you sell this option at this price, you need to make sure you're not gambling, right? You're just providing a service to a client. So, in which way? In other words, I'm asking how do you hedge this option, right? Under this ideal world, right? And if the candidate is good enough, surprisingly, if you are able to survive up to the third question, if the candidate is good enough to survive the third question, the next question will be, how does that relate to the Black-Scholes model? Okay, U and D, what does it mean? I mean, how do you calibrate that to the Black-Scholes model? Right, so I mean, from something that is simple, we'll be able to get deeper and steeper, step by step. And your job, when you're trying to look for, when you're trying to look for a job, is to make sure that you understand simple stuff to the bottom. Okay, in an intuitive way. Sometimes you think you understand it, but maybe you don't. Right? Like myself, when I come up, when I stand up, when I present something, when I write the slides, I mean a lot of concepts I thought I know. When I write it down, and I will try to derive the details because I'm going to be asked about the details, then I get stuck because for certain parts I'm not deep enough. I'm not to the bottom, and that's something that I want to recommend you to try to avoid. Try to prepare a little bit in a more solid way in terms of simple questions, because it's the simple things, it's the intuitive things that will make sense, that will make the connection. Okay, now back to this example. So it's a single step binomial tree, and we have stock and the interest rate, risk-free interest rate R, and we have two possible states, up and down. What is the price of the put option or call option at time 0? So the way we deal with that, we have multiple ways. One way to deal with that is to create a portfolio that replicates the payoff, right? So we take some position, delta shares in the portfolio, and we say that okay, my initial value of the portfolio is V0. The amount of cash in my portfolio is V0 minus delta S0. Okay, so what we want to achieve is that at time t, when the option expires, the portfolio value is equal to the payoff value, whether it is a call, it is a put, or it is any function of the final option stock value. It has to be equal to the upstate value. If the price goes down, it has to be equal to the downstate value. Okay, and then we look at this equation. We have two unknowns, right? The unknown is delta, we don't know. The other unknown is V0, right? It's the value of the option we don't know. And we have two equations. Just solve this linear equation. We have the solution, right? We have our delta, which is VU minus VD divided by SU minus SD. And we have our option value at time t0, which is the discounted value of this formula. And this formula, if you give it a name of the coefficients, because they really look like probability, right? If you give them a name, you give them the name called risk neutral probability. Okay? And you say that then under that artificial definition of a measure called risk neutral measure. My price is the expectation of my future payoff under that measure and discounted now. Okay, so here I want to emphasize that risk neutral probability is something that is artificial, that is created by mathematicians to make option pricing easier. Right? Nobody lives in a risk neutral world, right? You take risk, you get return, right? The reason that we use risk neutral is because our market is complete, right? It's because whatever I am pricing, I'm pricing a derivative, right? And I'm able to replicate this derivative by the underlying asset, right? If that is the case, you can assume that the value of the derivative is, you can assume that the value of the derivative is, it's not assume, it's, you can say that the value of the derivative is the expectation under the risk neutral measure of the value of the contract itself, or the value of the payoff itself. And you can also say that the diffusion of this underlying stock, of the underlying asset, is the drift of it is the risk neutral measure. It is really not, right? The stock doesn't, the drift of the stock is not risk-free interest rate. The stock of the drift is its own drift, right? Only when you try to price a derivative on top of this stock, you start to make the assumption of under risk neutral measure, your stock diffusion model is Black-Scholes and the drift is R, right? That's only valid if you try to price a derivative on this stock using expectation, okay? So why binomial tree model? It is overly simplified by the surprisingly general after extension, and you can have, well, start with two states. It's quite limited in terms of representing the final state of your stock price, but you can always have more final states, right? After extending the model to multiple steps. And you can handle many payoffs in option types. The only assumption about, the only assumption that we made to the option or to the payoff was that V is dependent on the terminal value of the stock at the expiry time T. So this V can be call, can be put, it can be any shape, any functional shape of this variable S capital T. And it is very natural for binomial trees to handle American options, barrier options that looks backward. And it's very easy to implement. But the cons, the disadvantage of this binomial tree model is that it is difficult to handle path-dependent options, like Asian options, because these options, it requires information before, right? When the tree is going from the backward, but if you need something before the current time, then it is difficult. Well, there are ways, but it is not straightforward to use binomial tree in that case. So we're gonna look at how easy it is to implement them, and we're gonna call it a day. So how easy it is to implement them? Option type, we have, so if we look at input, we have option type, call or put. We leave the room for extension for the future. And we have this option strike K, time to maturity T, and these are the attribute of options, right? These are attribute of the product. And we have the current value of the underlying S0. We have the risk-free interest rate R. These two are the market value, okay? And we have some weird up state and down state that we define under our ideal word SU and SD. So these are the inputs, and the output is option price. Okay, now here is how we implement it. We include some header file, IO string, that allows us to take input from the keyboard and print output to the monitor. And we include a header file called cmath which is for the exponential function. Okay, and there's an assert for us to validate the input. Okay, then we define our enum type, option type. It can be either call or put option. Now we specify, we declare these variables: strike, time to maturity, starting price, up price, down price, rate, value of the option when it goes up, value of the option when it goes down. And we ask for the inputs. Option type, 0 for call, 1 for put. You ask the user to key in from the keyboard, right? And from the keyboard, actually, it is not, well, call and put, how to represent that? It's an integer, right? So you ask 0 for call and 1 for put. And you take the integer that the user keys in. So you use stdcin input operator, meaning whatever I key in on my keyboard, it is going into the value of this variable option type. And then you make sure that whatever that the user is typed in, the user typed in is either 0 or 1, right? Otherwise, it's something that we are not able to interpret. So we want to throw exception here, right? We stop right away if it is not the case. And then we make a conversion, because this is an integer, we make a conversion to the type that we define, enum, right? We convert this type integer because this enum is intrinsically integer. This is 0, this is 1, right? So we make a conversion. So call for 0, 1 for put. And then we ask for strikes. Tell me the strike, and then I take the strike from the input to k, and ask for time to maturity, and then take it to t. Ask for the current price of the stock, take it to S0. Ask for the risk-free interest rate, take it to rate. And upstate, downstate, same thing. And then after that, so we are done with the user interaction, right? So here it is lengthy because we are interacting with the user. Or instead, if you just define the variable, assign them values, it will be much shorter. So the actual code of binomial tree happens here, right? So first of all, we calculate our risk neutral probability, which is exponential RT minus SD, well, divided by SU minus SD, right? This is following our previous formula. And then we calculate our VU and VD, right? If the option is a co-option, we check if the option size is large, so if the stock is larger than the strike, it's S minus K, otherwise it is 0, right? Same for the downstate. And for put, if it is less than K, K minus stock price, otherwise 0. So this is for the final payoff. And the calculation of the option price is just one line. That we take the conditional, we take the probability and the risk neutral measure, and we discount. Okay, so V0 is our option price for this one-step binomial tree. Okay, I'm gonna stop here, and the follow-up will be, we try to bridge Black-Scholes model and the binomial tree model, and following that, we will look at the features of the language about arrays and loops, those kind of stuff. Any questions? Sorry for keeping you late. Any questions? No?